suppose that I take a metal plate and I have a wire attached to that metal plate, and then I take another metal plate, basically like the same kind of size, and I put it really close to the first one, and it also has a wire attached to it. Then I have made a device which is called a capacitor. So a capacitor is in some ways the joule of the inductor. So it's similar to an inductor, but the roles of current and voltage are the other way around. So in a real capacitor, they look like pictures you see on the left-hand side here. In a real capacitor, you would often have these plates which are kind of curled up around each other to get a large surface area. But you can make a basic capacitor just with these little plates. So let's run through a few properties of capacitors. So energy is stored in an electric field. So if I had applied a voltage across this device, so put a voltage on these wires, then there will be a little electric field that forms, kind of connecting these plates together. So this is the electric field, and that will store energy in the same way that an inductor's magnetic field stores energy. In a capacitor, it's an electric field. So energy is stored in an electric field. The other key, or the kind of main defining property of a capacitor is this equation. So capacitors are described by that the current in a capacitor is equal to a parameter called C, the capacitance, times dV dt. So it's the other way around to the inductor equation. So it's the change in voltage which causes a current or allows a current to flow through the capacitor. Or if there is a current flowing, then the voltage is changing. You can kind of read this in both directions, read the causality in both directions. So this is the governing equation for a capacitor, and it's one that you need to know. Let's define these terms, where IC is the current flowing through the capacitor. V is the voltage across the capacitor, and C is the capacitance. So the capacitance, C, is measured in farads. In farads with the letter F. So as an example, you can just read it on the capacitor in the photograph here. That is a 22 microfarad capacitor. The voltage there is a maximum rating. So for some types of capacitors, they can only survive a certain voltage. This one here is rated to 50 volts. While we're talking about what real capacitors look like, one important thing to highlight, this particular type that look like this, these are electrolytic capacitors, and they have to be connected with a positive and negative the correct way around. So the negative is indicated with these little kind of minus signs that you see in the dash here. So in the photo on the right, you can see that indicates the negative side. So you connect that to the negative voltage. And then your capacitor will operate correctly. So that's true for some types of capacitors, but not others. Some are said to be polarized, like these ones. Polarized meaning you have to get the positive and negative terminals the right way around. Some are unpolarized, in which case they don't care. So capacitors are described by this equation. So I see the current in the capacitor is C dV dt. The circuit symbol is basically if you took the parallel plates and kind of looked at them side on, then this is what you would get. So circuit symbol is that. There is a voltage and a current. So we again use passive sign convention. So the current is going from positive to negative. So that's the circuit symbol for a capacitor and the equation that describes it. So let's talk a little bit sort of intuitively about what a capacitor does in a circuit. So intuitively, a capacitor tries to, and we'll make this precise in a moment, but tries to maintain a fixed voltage. Okay, so more precisely, it acts as a temporary current source to counteract any change in voltage. So for example, you will often see them in real circuits where you have, some node which is connected to, maybe there's like a power supply, and maybe it connects into some load which, which is doing something in this circuit, and we have a ground path, and you might take this power supply and you might put a capacitor between it and ground. And then the voltage here, which is the voltage of this power supply, will then tend to be stabilized by the capacitor. So that's a very common kind of real-world use of this circuit element. But as far as analyzing it, this is the really important equation that we need to understand here. And similarly for inductors, we can actually integrate this one to get to an expression for the voltage. So let's have a look at doing that. So given that current is C dV dt, we can also solve for the voltage. So to do that, we need to integrate both sides. So similarly to what we did before, integrate with respect to time both sides. So this would give me dV dt dt, and again I'm going to take some limits of integration, so let's say 0 up to some time t. The expression on the right hand side can be simplified. I can bring the capacitance over, so 1 over c integral I. Just to make this super clear, I'm going to write I of t. We're talking about a time dependent function here typically, and then on the right hand side, just putting in the limits of integration, I'll end up with that. So our expression for the voltage on this capacitor is then 1 over c integral 0 t I of t dt plus v of naught. So this is similar to the equivalent expression for an inductor, but we've swapped the role of voltage and current. So again, this is an important equation, and you should either know it or be able to derive it as I just did here in a couple of lines. The most important kind of fundamental definition that you need to remember is this one, that the current in the capacitor is C times dV dt.